Hi everyone, in this video we will learn about parametric surfaces and how to find their areas. So the basic idea is similar to any parameterization that we have dealt with in this course or that you have seen in Calc 3 before, and it is to reduce the number of parameters or reduce the number of descriptive variables needed to sort of generate an object like a surface. So for example, a parameterization could be in terms of the variable u and v, where they're broken into x as a function of u and v in the I direction, y as a function of u and v in the j direction, and z as a function of u and v in the k direction. When you were in two dimensions, you could parameterize using a time variable t, right? So when you're parameterizing in this manner, you can always reduce the number of functional variables by 1. And what happens is as uv moves in its own domain, each pair will generate a vector of this form in R3, and the set of all those vectors will form a surface which is called a parametric surface. So diagrammatically, what is going on here is something like this. So you have 2 space and 3 space. The 2 space is the space of the parameters u and v. And suppose the parameters u and v have a domain D, which is given roughly described in this way, and this is the domain for parameters, and this is some specific point uv in the parameter. Now what this uv corresponds to is this r, the position vector. It is going to map to some vector, right? Some position vector, which means it's going to map to some point in space through this position vector r, and this position vector r is ruv. So each point in this 2-dimensional plane uv gets mapped to a point in the 3-dimensional world through a vector r, which is a function of u and v. And if you repeat this process through the entire domain, you end up with some surface in 3 dimensions. So for each element in the domain D, you get a point on the surface S through the position vector R. Let's look at an example and also learn a generic way of how to map this given domain D into a surface S. In this example, it says identify and sketch the surface with a vector equation in parametric form given by 2 cosine u I cap, v j cap, and 2 sine u k cap. So in the parametric form, the equation, the relation we have is x is 2 cosine u, y is v, and z is 2 sine u. Now immediately, one thing that we observe is x and z have cosine and sine with the same coefficient 2, which means that if I square these and add them up, I expect something nice to happen, and it does happen because I get 4 cosine squared u plus 4 sine squared u, which is 4. So we get a relation between x squared and z squared being equal to 4, which we know from our prior knowledge of 3-dimensional shapes is a cylinder / it's a circle in the xz plane. So what we have is a circle in the xz plane, which we know in 3 dimension becomes a cylinder. So if I try to plot this out, I have x, y, z. So in the xz plane, I have already found a circle of radius 2. So this is 0, 0, 2, and this point would be 2, 0, 0. Now let's look at y. Now what happens to y is simply equal to v, that there is no restriction, which means we're only moving parallel to the y-axis. And that's where we get this entire cylinder. So the surface being represented here is the the surface of a cylinder. Yeah, that shading is not very helpful, but you get the idea. The second part of the problem says what happens if we restrict u to 0 to pi over 2 and v to 0 to 3. So what that does is it simply restricts each of your elements. So u between 0 and pi over 2 means that the angle we're only working with one section of the angle, like 0 to pi over 2. So it's not a full circle, it's a quarter circle. And v between 0 and 3 means we're also stopping at cutting this off at 3. So this restricted part, if I have this restricted surface, then the shading of this restricted surface will include just this part. So it will be it'll be like this curved section of the cylinder that involves half rotation or a quarter rotation of a circle and a linear distance of 3. Now, how do we, is there a way for us to generally understand what is going on, right? So whenever we're trying to map one into the other, what we want to look at is some very specific family of curves. So for example, the two main things that we want to consider are what happens when u is constant and what happens when v is constant. And why is that? If you look at these two worlds, the two-dimensional parametric world and the three-dimensional world, so over here, we want to break this down into a vertical analysis of u equals u naught. So what happens when we have this red constant u? If I move along u equals u naught and change the value of v, what does that correspond to on the surface here? And why that helps is it gives us a understanding of how this line relates to some constant. So maybe this u equals u naught corresponds to this red line over here. Whereas if I go across and I have v equals v naught, so considering what happens when v is constant, and that gives us some other cross section. And from there, we obtain that every point u naught v naught becomes, in this other world, that's the vector pointing to r u naught v naught. So some of these curves, specifically u being constant and v being constant, gives us an understanding of how things are changing in the three-dimensional, in the actual object. Right? And the last thing that you want to take note of is if you have a surface z equals fxy, this can automatically be parameterized by x equals y, x equals x, y equals y, and z equals f of xy. This is already reducing the number of controls from 3 to 2. So let's look at a question which is slightly different, which says parametric representation of the cylinder given by x squared plus y squared equals 4 and z between 0 and 1. So this is, because this is a circle, we know that the best parameterization we have is cosine theta and sine theta. And z is just z, but between 0 and 1. So the parameterization here, the uv, the role of uv would be played by theta and z, and we would write this as 2 cosine theta I cap plus 2 sine theta j cap plus z k cap. Now let's look at another example where we are asked to find the parametric representation of the surface z equals to 2 times square root of x squared plus y squared. And this in this case is it's a cone. The top half of the cone, z squared equals 4x squared plus 4y squared. So there are two solutions here. The simplest parameterization is, because it's a surface, I can use x equals x, y equals y, and z equals 2 square root x squared plus y squared. Right? So in this case, the role of u and v are being played by x and y, and you just have xi cap plus yj cap plus square root 2 square root x squared plus y squared k cap. But there's another solution. The second solution is if we are to use r and theta as parameters. So I can set x equals r cosine theta, y equals r sine theta, and z will become 2 square root r squared sine squared theta plus r squared cosine squared theta, which will come out to be 2r. So in this case, our parameters are r and theta, so the position vector is given by r cosine theta I cap, r sine theta j cap, and 2r k cap. Okay, so solution 1 is not really very much helpful in problems because we're not changing anything, right? Whereas the second way of doing the parameterization can be helpful. And let's look at how does this mapping look like from 2-dimension to 3-dimension, just to get an idea of those constant lines that we looked at earlier. So we have a parameterization using theta and r, and we have a rectangle going from 0 to 2 pi for theta and 0 to 1/2 for r, and that's my region D here. And over here, I know that the surface that I'm dealing with is a cone. So I have a cone here. Oh. And okay, so let's see, what does this line look like? Right, so this line is r equals some constant, right? So suppose r naught. If I move along a constant radius on this cone, it's going to map out a circle. So that's going to be r equals r naught on the cone. And if I take a vertical line, which is theta equals theta naught, a constant, theta equals theta naught is going to be a line that just cuts through the side of this cone, theta equals theta naught. And so the rectangular coordinates here sort of become the two basic shape, and you can imagine if you take a bunch of these slanted lines and move it along the circle, you will generate a cone, which is why you have a cone on the right hand side. That's it for this particular video. In the following video, we're going to look at something that you have seen in Calc 2, which is surfaces of revolution. And we'll also look at tangent planes and a few more results that have to do with parametric surfaces, ultimately culminating with how to find areas of such surfaces when they are presented in parametric form. But that's it for this video. Thanks everyone.